By the late 1970s, Soviet radar networks stretched 1,200 kilometers deep, and any American bomber that entered faced over an 80% chance of being destroyed. So the Pentagon posed an almost impossible question. Could you build a full-size bomber that disappears from radar? The answer cost roughly $2 billion per aircraft. It didn't overpower detection. It exploited a fundamental weakness in how radar actually works. Soviet air defense in the late 1970s was a fortress of sensors and missiles, stretching from Eastern Europe to deep inside Russian territory. Radar sites blanketed the landscape in overlapping arcs, each one capable of detecting a high-flying bomber from as far as 600 to 1,200 kilometers away. Every American B-52 or similar aircraft that crossed that threshold was almost guaranteed to be tracked, classified, and intercepted. The probability of a successful penetration was grim. Exercises and classified simulations estimated that over 80% of bombers would be destroyed before reaching their targets. This reality forced a reckoning in Washington. Relying on speed, altitude, or sheer numbers had reached its limit. The Strategic Air Command's entire concept of deterrence was at risk. A single radar contact could trigger a chain reaction. Surface-to-air missiles locked on, interceptor squadrons scrambled, command centers alerted across the Soviet Union. Each new generation of radar grew more sensitive and more difficult to jam or deceive. The United States needed an answer that didn't just survive the radar wall, but slipped through it, unnoticed. In 1979, the Pentagon launched the Advanced Technology Bomber Program. The goal was radical: develop a bomber that could cross the most heavily defended airspace on Earth and survive. The challenge wasn't just building a new airframe. It meant rethinking every assumption about how aircraft interact with radar and finding a way to make a full-sized strategic bomber nearly vanish from the electromagnetic spectrum. This was the beginning of a project that would ultimately produce the world's most elusive aircraft. On July 17, 1989, the B-2 prototype, designated YB-2 and bearing serial number 821067, lifted off from Edwards Air Force Base for its maiden flight. The aircraft's 44-meter wingspan stretched across the California sky, a seamless, unbroken arc unlike any bomber built before. Instead of a fuselage and tail, the entire platform was a single, continuous wing, an idea first imagined by Jack Northrop in the 1940s, now realized with the help of digital flight controls and composite materials. The test team kept the landing gear down for safety, but the flight itself was a validation of radical engineering. Fly-by-wire systems, essential to stabilize a pure flying wing, translated the pilot's commands into tiny, precise adjustments, correcting for the natural tendency of the design to yaw and pitch unpredictably. With this technology, the B-2 could fly as smoothly as any conventional bomber, but with a shape that offered almost no sharp edges or vertical surfaces for radar to latch onto. The man at the controls, test pilot Major John Thomas, guided the YB-2 through a cautious 2-hour circuit. Every minute in the air was a proof of concept that a full-scale operational flying wing could be built, flown, and controlled with precision. The size alone was astonishing, 44 meters from tip to tip, yet its profile on radar would be closer to a bird than a bomber. This flight was the moment the B-2's promise left the drawing board and became a reality, ushering in a new era of stealth aviation. The technical achievement set the stage for the next challenge: understanding exactly how radar detects aircraft and why this new shape could change the rules. Every radar system works by sending out a burst of electromagnetic energy, what's known as a pulse, then listening for the echoes that bounce back from objects in the sky. When that pulse hits an aircraft, metal surfaces, engine faces, and even landing gear reflect some of the energy straight back to the radar. The strength of this return is measured as radar cross-section, or RCS, and it's expressed in square meters. A larger RCS means a louder echo, making the target easier to spot and track. For a sense of scale, a B-52 bomber, long the backbone of the U.S. strategic fleet, registers an RCS of about 30 square meters. That's roughly the size of a billboard, and it makes the B-52 a bright, unmistakable target for most air defense radars. But for an aircraft to slip past modern fire control systems, the RCS needs to be drastically lower. According to declassified Air Force specifications, the threshold for reliable detection by advanced Soviet-era radars hovered around 0.1 square meters. At that level, a bomber's signature would blend in with ground clutter or even resemble a large bird on the screen. Lieutenant Colonel Ortiz, a radar systems analyst, described 0.1 square meters as the practical cutoff. Anything above that gets classified as an aircraft. Anything below becomes difficult to distinguish from noise. This benchmark set the design bar for stealth. To survive, a new bomber had to shrink its radar cross-section by 2 orders of magnitude compared to its predecessors. The search for a solution would soon focus on geometry, materials, and every detail that influences how radar energy scatters or gets absorbed. The B-2's stealth begins with its shape. The bomber's flying wing design isn't just for aerodynamics. It's a deliberate strategy to redirect radar energy away from its source. Unlike traditional aircraft, which have vertical tails and upright control surfaces that bounce radar waves straight back, the B-2's smooth, continuous arc offers almost no flat surfaces facing any single direction. The principle is rooted in the cosine square law. The amount of radar energy reflected depends on the angle between the radar beam and the aircraft's surface. With the B-2, most incoming waves strike at shallow angles and scatter sideways or upward, not back toward the radar. But even a perfect wing can't avoid every sharp edge. Maintenance panels, access doors, and structural seams are unavoidable. To prevent these from becoming bright spots on a radar screen, engineers gave the B-2 its distinctive sawtooth edges. Each panel seam is broken up into a series of shallow, zigzagging facets, each just a few centimeters wide. When radar hits these edges, the energy splits into multiple weaker reflections, spread over a wide range of directions. This diffusion effect can reduce the radar return by up to 12 decibels compared to a straight edge. The result is dramatic. Where a conventional bomber might appear as a 0.5 square meter target at certain frequencies, the B-2's geometry alone can cut that signature by an order of magnitude. The aircraft doesn't vanish from radar, but its echo becomes so faint and scattered that most tracking systems can't lock on until it's already close. Geometry forms the first wall of invisibility, laying the groundwork for what comes next. Materials that absorb the radar energy outright. The B-2's low observability hinges on more than just shape. Its skin is engineered to absorb radar energy rather than reflect it. Dr. Mira Chen, a materials scientist involved in composite development, describes the surface as a layered shield, each layer tuned to convert incoming electromagnetic waves into harmless heat. The foundation is a carbon fiber composite, but what sets the B-2 apart is the radar-absorbent material, or RAM, applied in precise layers just 150 to 80 microns thick. This RAM isn't a simple coating. It's a hybrid of carbon nanofibers and ferrite particles, each chosen for their ability to interact with different parts of the radar spectrum. Carbon nanofibers form a conductive network that disrupts the electric field of the radar pulse, a process known as dielectric loss. Ferrite particles, meanwhile, respond to the magnetic component, converting energy through magnetic dipole relaxation and eddy current damping. Together, these mechanisms can absorb over 90% of incident radar energy across both X and Q band frequencies, the most common bands for air defense radars. The thickness of each layer is carefully calculated. Thicker coatings line the leading edges where radar exposure is greatest, while flatter panels get a thinner application. This graded approach ensures that the impedance of the surface matches free space as closely as possible, reducing reflections. The result is a bomber whose radar cross-section drops well below the critical 0.1 square meter threshold, pushing it toward the limits of what most tracking systems can reliably detect. The material science behind the B-2's skin is as essential as its geometry, forming the second wall of stealth and setting the stage for the next challenge, shielding engines and masking heat. Burying the B-2's 4 engines deep inside the wing wasn't just a design flourish. The S-shaped inlet ducts twist out of sight, hiding the spinning compressor blades, prime radar reflectors, from view. Lined with radar-absorbent material, these ducts soak up and scatter radar energy, especially in the bands most air defense systems rely on. Any pulse that makes it inside is trapped before it can bounce back, leaving little for enemy screens to detect. Infrared sensors pose a different challenge. Jet exhaust glows hot, but the B-2 cools its plume by mixing it with ambient air inside the wing, then spreading it over wide, flat surfaces. This approach drops the exhaust's temperature by up to 70% compared to older bombers, making the B-2's heat signature faint and lock on by heat, seeking missiles much harder. These weren't just lab tricks. On October 1, 1997, the B-2 entered service. By 1999, it flew combat missions over Kosovo, bypassing Soviet-built radar. The real test came on October 15, 2001. B-2s launched from Missouri, struck Afghanistan, and returned 44 hours in the air. Radar operators described the B-2's return as a faint blip, sometimes no bigger than a bird. The often cited 0.01 square meter radar cross-section isn't invisibility, but it's enough to slip past most defenses until it's too late. Commander Ethan Vale summed it up. The B-2 isn't a ghost. It just makes you look twice at every shadow on your screen. Stealth is no longer science fiction. It is a measurable advantage in modern air power. As radar, infrared, and detection networks evolve, the fundamental physics behind low observability still define strategic balance. The edge is never permanent, only engineered, tested, and fiercely protected. Share your perspective below.